In the previous lecture, we have discussed different methods of determining inverse Laplace transforms. So in this lecture, we will introduce the concept of convolution. This has a lot of applications, but in this lecture, I want to make you familiar with the concept of convolution, especially for the Laplace transforms. So the statement of convolution theorem is, if the inverse Laplace transform of a function fs is equal to ft, and if the inverse Laplace transform of a function gs is equal to gt, so then the inverse Laplace transform of a function fs times gs can be represented in the integration form, the integration from 0 to t fu times g of t minus u du. So this f star z is called the convolution of a function f and g. So let us look at the proof of this theorem. So to prove this result, we consider a function phi t equal to integration from 0 to t fu times g of t minus u du. So if we take the Laplace transform of this function phi t, and if we use the definition of Laplace transform, that can be represented as the integration from 0 to infinity e raised to the power minus st, and in the curly bracket we have mentioned the function, that is the integration from 0 to t fu times g of t minus u du, and then we are integrating it with respect to t. So we want to use the change of order of integration. So I have explained you in this figure, the domain of integration for this double integral is the entire area lying between the lines u equal to 0 and u equal to t. So on changing the order of integration, we obtain this expression. So the Laplace transform of a function phi t can be represented as 0 to infinity, the integration from 0 to infinity, and the integration from u to infinity. So we are basically integrating the limits we are taking t equal to u to infinity, and the limits we are taking for u equal to 0 to infinity here. So that I have already explained you in this figure, that why we are taking the limits t equal to u to infinity and u equal to 0 to infinity. And the integrand we have that e raised to the power minus st times fu times g of t minus u. So to integrate this, what we are going to do here is that we are going to write e raised to the power minus su and e raised to the power su. We have just considered this term e raised to the power minus su and e raised to the power su, and if you observe here in this equation, since e raised to the power minus su and f of u, a function f of u, is independent of t, so I can take it from outside from this integration. So I can write I am writing this equation in this way, that 0 to infinity e raised to the power minus su times fu, and then in the curly bracket we are integrating from u to infinity e raised to the power minus s, which we have taken it common, and in the bracket we have I'm mentioning the t minus u times g of t minus u dt, and then finally we are integrating it with respect to u. So again I am substituting it here. So I am considering this t minus u equal to some another variable nu here. So then dt is going to be equal to d nu, and the limits will also be changed. So at t equal to u, v will become here 0, and at t equal to infinity, v will become infinity. So then the last equation will become here, that the Laplace transform of this function phi t is equal to integration from 0 to infinity e raised to the power minus su fu, and inside this curly bracket I have written 0 to infinity e raised to the power minus s nu times g nu d nu, and finally we are integrating it with respect to u here. So again in the next equation we have integration from 0 to infinity e raised to the power minus su fu, and what we have in the last equation in the curly bracket, that's nothing but the Laplace transform of a function g nu. So I have just mentioned it here, that in the curly bracket the Laplace transform of a function g nu, and then finally we are integrating it with respect to u. So what is this L of g nu? That in this statement of a theorem we already know that that is equal to gs here. Okay, so then I'm just in the place In the place of L of G nu, I am just writing it capital GS. So we have this equation that integration from 0 to infinity e raised to the power minus SU times FU times G capital GS times DU. So again, if you observe here that capital GS is independent of U, so I can take it outside from this integration. So in the curly bracket, I am writing it here, integration from 0 to infinity e raised to the power minus SU times FU du, and outside this I am again writing this GS. Now again, if you observe here that this, what is this in the curly bracket we have here, this is nothing but the Laplace transform of a function ft, and that we have assumed it here, that is nothing but equal to fs here. So now if we take the inverse Laplace transform here, so this equation takes this form, that the inverse Laplace transform of fs times gs will become phi t. And what is our function phi t here? That was nothing but, it was considered in the integral form, and that is nothing but your integration from 0 to t fu times g of t minus u du, and that's the proof of this convolution theorem we have. So let us look at some examples where we are going to use the convolution theorem to solve the problem. So the first problem we have is that we want to evaluate the inverse Laplace transform of the function s over s square plus a square whole square. So there are many ways to compute the inverse Laplace transform of this function here, but here we are going to use the convolution theorem to evaluate the inverse Laplace transform of this function. So since we know here that the inverse Laplace transform of a function s over s square plus a square equal to cos at, we already know these formulas, and the inverse Laplace transform of a function 1 over s square plus a square is equal to 1 over a sin at. So now I am going to use the convolution theorem here. So to use the convolution theorem, I am going to take the product of these two functions, s over s square plus a square and 1 over s square plus a square. So then the inverse Laplace transform of s over s square plus a square times 1 over s square plus a square, if you use the convolution theorem, can be written as integration from 0 to t cos au times 1 over a sine of a, in the bracket we have t minus u du. So why we are taking this? Since f of u is equal to cos au and g of t minus u is nothing but 1 over a sine of a t minus u here. So we cannot directly integrate this integrand here. So what we are going to do is that we are going to use some trigonometric formulas to express this function, to express this integrand in terms of this sine at, so sin c minus sin d. So we are going to use this formula sin c minus sin d, and then which is nothing but your, all of you know here, that is nothing but your 2 cos c plus d by 2 and sin c minus d by 2. So if we compare these values, that means c plus d can be written as 2 au and c minus d can be written as 2a times t of t minus u. So if we solve these two equations, we will obtain the values of the c, which is nothing but your a times t, and d is equal to 2au minus at. So I am going to express the integrand in terms of this trigonometric formula, that means sin c minus sin d. So if we just substitute the value of c and d in this expression, so we will have the equation that 1 over 2a integration from 0 to t sin at minus sin 2au minus at. Again we are integrating this expression with respect to u. So now if we integrate it here, so the integration will takes this form, that 1 over 2a sin at, we will take this outside and we will integrate the constant term, that means 1 times du, so it will become u, the integration from 0 to t, plus the integration of sin 2au minus at will be your minus cos, so minus minus will become plus, and that will give you this cos of 2au minus at over 2a integration from 0 to t here. So if we simplify these things here, substituting the limits, and if we simplify it here, we will obtain this expression that 1 over twice a times t sin at. So the inverse Laplace transform of a function s over s square plus a square whole square is equal to 1 over twice a times t times sin at. Let us look at another problem of evaluating the inverse Laplace transform of a function s square over s square plus a square times s square plus b square. So again, there are many ways to evaluate the inverse Laplace transform of this kind of function, but here we are going to use the convolution theorem to evaluate the inverse Laplace transform of this function here. So we already know that the inverse Laplace transform of s over s square plus a square is equal to cos at, and the inverse Laplace transform of s over s square plus b square is equal to cos bt. So then if we use the convolution theorem, so that means if we take the product of these two functions, so L inverse will become the inverse Laplace transform of s over s square plus a square times s over s square plus b square can be represented in this integral form. That means integration from 0 to t cos au cos b times t minus u, and with respect to, we are integrating it with respect to u. Why we have taken this cos au? Since our ft is cos at, so fu will become cos au, and our gt is cos bt, so g of t minus u will become cos of b of t minus u. There is a mistake. So g of u, this is not g of u, that's going to be a g of t minus u is equal to cos of bt minus u. So now if we integrate this expression here, so it will become 1. So again we are going to use the trigonometric formulas here to represent it in this form of cos c plus cos d. So we will evaluate the things of c and d in the same way as we have done in our previous example. So it can be represented as 1 over 2 integration from 0 to t cos of a minus b times u plus bt, and the same thing we have that plus cos of a plus b times u minus bt. We are integrating it with respect to u. So if we integrate it here with respect to u, so we will have this expression that sine of a minus b times u plus bt over a minus b. The limits are from 0 to t, plus if we integrate the second term, so it will give you sine of a plus b times u minus bt over a plus b, the integration from 0 to t. So when we substitute the limits in the place of this u here, so we will obtain this expression that 1 over 2 sine at minus sine bt, some of the terms will get cancelled over a minus b, and again if we substitute the limit 0 and t in the place of u, we will have sine at plus sine bt over a plus b. Now if we take the LCM, so and if we simplify it here, some of the terms will be cancelled out. 2 will also be cancelled, and the final expression we will have is that a sine at minus b sine bt over a square minus b square, which is nothing but the inverse Laplace transform of a function s square over s square plus a square times s square plus b square. Thank you very much.